So we're looking at simplifying rational expressions, and so our first step is going to be to factor both the numerator and the denominator, and then we're going to divide out any common factors. So looking at this example B here, we need to factor. So the first part, the numerator, can be factored as a difference of squares. I've got two perfect squares there, so it's going to be k plus 3 and k minus 3. Then the denominator is a trinomial with coefficient 1, so I can factor that with two parentheses with a k in the first spot, and then we're going to look at the 6. Note that I'm going to need two negatives to multiply to a positive 6 and add to a negative 5. So what goes into 6? 2 and 3. 2 and 3 add to 5, so that's going to be perfect. We can check it. Oops, I said 2 and 3. 2 and 3, okay. So if I check it, negative 2 plus negative 3 is negative 5, and negative 2 times negative 3 is positive 6, so it works. Any common factors we have, we're going to divide out. So my k minus 3 and my k minus 3, we're going to divide those out. And what's left is going to be k plus 3 on the top over k minus 2 on the bottom. Okay, let's try some more. Let's look at part C. That one starts off with the top being a binomial, two terms, but it's not a difference of squares. There's no square. So instead I'm going to look for a GCF, something in common to take out. And notice I can divide them both by 3. The first term is negative, so we're going to divide out a negative 3. Okay, so it's going to leave us with 5x, and then 6 divided by negative 3 is minus 2. On the bottom, that is difference of squares. It's two terms again. They are all perfect squares. So I'm going to use the difference of squares and factor that as 5x plus 2 and 5x minus 2. Now both numerator and denominator have the factor 5x minus 2, so those will divide out, and my answer is going to be negative 3 divided by 5x plus 2. Alright. In the next one, I'm going to start at the top. It's a trinomial, coefficient 1. So I'm going to start it off with an x in the beginning of each parenthesis. Then we're going to look at this 12. It's negative, so I need one negative and one positive. And I need the results to add up to negative 1. So 3 and 4 go into 12. If I want it to add up to negative 1, the 4, the larger one, needs to be the negative. So we'll check. Negative 4 plus 3 is negative 1, and negative 4 times 3 is negative 12. On the bottom, that doesn't look right now like it can be factored, but notice that it's not written in the right order. So let's rewrite that. It should have the x first. So if I rewrite that, and notice that the x is negative, I've got negative x plus 4. Now I notice that I can factor, I'm going to factor out that negative since I have a negative leading coefficient. So if I factor out the negative, it's going to give me x minus 4, just dividing by that negative. So negative divided by negative is positive, and a negative, positive divided by a negative is negative. Okay? I needed to factor that negative out to be able to have two factors of x minus 4 that I can divide out. So my answer looks like it's going to be x plus 3 over negative 1. Now that's not a proper way of writing something. We know that anytime you divide something by a negative 1, it's going to make the thing negative. So we're going to write this as negative x plus 3. This will be fully simplified. Right, to divide something by 1, you'll get the same thing, but if you divide it by a negative, it's going to change the sign. Alright, at the bottom of this page, you've got a note. It's very important to notice what we don't do in these problems. We never reduce without making sure the problem is factored first, and that means that we only cancel factors, never the terms. Okay, so an example is if I have something like x plus 1 over x plus 1 times x plus 2, okay, a factor is an entire unit. So my x plus 1 factor is going to cancel with the x plus 1 factor. That entire group will cancel to leave me with 1 over x plus 2. So this is okay. What we don't do is look at an expression like how about x squared plus x plus 4 over 2x squared plus 3x plus 8? It's not okay to say, well, the x's are going to cancel here, it's going to leave me with a 1 and a 2. The 4's are going to cancel here, leave me with a 1 and a 2. The x's cancel here with a 1 and a 3. That doesn't work. Okay, it's only the entire groups, the entire factors that cancel. And if you would like an explanation for a reason for this, when we're looking at regular fractions, we know it's okay to say something like 12/18 is going to reduce because it's 6 times 2 and 6 times 3. And we're going to divide both top and bottom by 6, and we're going to get 2/3. Okay? It's not okay to say something like 12/18 equals 10 plus 2 and 10 plus 8, and then cancel the 10s. I mean, you can't cancel parts of addition and then say it's equal to 2/8 or 1/4. I mean, that is not true. So you have to make sure you cannot cancel terms. Terms are part of addition, so never do this. Only cancel once they're part of a product. And that's the reason, again, why it's very, very important to factor making something part of a product. Alright, objective 3, we've got an application. So a company is manufacturing bicycles. So the equation for their cost, okay? So X is the number of bicycles, C is the cost to manufacture each bicycle. So what we want to find first is the cost when manufacturing 500 bicycles. So the cost is going to be 100 times X, which is going to be 500, plus 100,000, divided by 500. So let's grab a calculator and plug that in. 100 times 500 plus 100,000, and then divide that by 500 gives us 300. Alright, so this is, it's going to cost them $300 per, remember I can use that slash for per bike. Right, that's the cost to manufacture each bicycle. Okay, so it costs them $300 to make a bike if they're going to make 500 bicycles. Part B, let's find the cost for manufacture 4,000 bicycles. Okay, so the cost is 100 times 4,000 plus 100,000 divided by 4,000. And let's plug that in. So do you expect that it's going to be larger or smaller when I plug in the bigger number? 100 times 4,000 plus 100,000 divided by 4,000 is 125. So it's going to cost them $125 per bike if they make 4,000 bikes. Okay, so the cost per bicycle is going to decrease as more bicycles are manufactured. Right, so this is just an example of how rational equations are used in the real world of manufacturing and so on. And the company might want to do more with this equation and talk about their cost and their profit and how to maximize their profit or minimize their cost. So those are some things that we're going to look at as we go on further in this chapter. But it's one example of a real world application of a rational expression. And that's the end of the section.